Hello, in this video I'm going to solve this problem here. So I'll first just read the question. So we have two particles which move in a uniform gravitational field with an acceleration g. And at the initial moment the particles are located at one point and they move with velocities v1 and v2 horizontally in opposite directions. And the question is asking us to find the distance between the particles at the moment when their velocity vectors become mutually perpendicular, so perpendicular to each other. So the first thing to note about this question is the fact that it says uniform gravitational field. So that means that both the particles experience the same downwards acceleration of g. So that's important to remember. So we can draw a diagram to represent this problem. So if we say that this is the point where both the particles start off at, and we know that one particle moves in one direction, so I'll say this way, and the other particle moves in the opposite direction. And now I'm going to use some notation here to show the directions. I'm going to call this direction positive I, and that's a unit vector, which I will explain in a bit. So the opposite direction would be negative I, and I'm going to call the downwards direction positive J. And these are all unit vectors. So the way to understand unit vectors is just imagine we have any vector, so we'll say the vector A, and you know that vectors have magnitude and they have direction. So if we take this vector and we divide it by its magnitude, so that's A with the magnitude sign. So if we divide a vector by its magnitude, the thing that's left is its direction, and that is what we call as a unit vector, and it's only a lowercase with a hat. So unit vectors always have a magnitude of 1, and they just have direction, and we normally use I to represent horizontal unit vectors, J and J to represent vertical unit vectors, so the vertical direction and the horizontal direction. So on our diagram, so we can label V1, the velocity of the first particle, as being this way, and V2 as this way. And another really important part of this question is the fact that it says the two particles move with velocities horizontally in opposite directions. So from that we know that initially both particles had a vertical velocity of 0, so they didn't have any vertical velocity. But we know that by the end, when their velocity vectors are mutually perpendicular, because they are travelling in a uniform gravitational field, they will have a vertical velocity. And we know that because they both started off at 0 meters per second, like vertically, we know that by the end they will have the same vertical velocity because they're travelling in a uniform gravitational field. So we can draw out the path of these two particles, and we know that by the end they're going to look something like this. So V1 started off like this, and by the end it's going to have changed to something like this, and V2 is going to have changed to something like this. And we know that at this point these two vectors are perpendicular to each other. So I'll just draw the perpendicular. Yeah, and we can call these two vectors something else. So we'll call this one V1 prime, and I'll call this one V2 prime. So the first thing that we need to do to solve this question is to form some equations relating V1 prime with the original horizontal velocity V1. So what we can do is say V1 prime is equal to its horizontal component and its vertical component. So we know that its horizontal component hasn't changed over the course of the problem, and it's going to have stayed as V1. But because we're writing it in vector form, we need to turn this into a vector, and to do that we can just multiply it by the unit vector I, because it's in the positive I direction. So we'll say it's V1I. And then its vertical component, it's this vertical component here, we'll call the vertical component V for vertical. And again, we need to change that into a vector, so we will multiply it by its unit vector. So it's J. Yeah. And similarly, we can write an equation for V2 prime. So it will be its original horizontal velocity, which is V2, and we need to multiply it by its unit vector, which in this case is minus I, so it will be minus V2I. And its vertical component is the same as the vertical component for V1 prime, so it's the same VVJ. Okay. So another thing that we're going to need to solve this question is the concept of the dot product. And we know this because the question asked us to find the distance between the particles at the moment when their velocity vectors become mutually perpendicular. So the important bit is perpendicular. So first we need to understand what a dot product is. So if you have two vectors, so I'll just draw two vectors here. So here's one vector, we'll call that A, and we have another vector B, and say that these two vectors have an angle of theta in between them. We can do something called a dot product, so A dot B, and this is equal to A, B, their magnitudes, cos theta, where theta is the angle between A and B. And the way we can apply that here is we know that I and J, the unit vectors, so if I draw I and J, I'll draw it over here. Here's I, and here's J. We notice that the angle between them is 90 degrees. So if we were to do a dot product of between I and J, so if we do I dot J, we see that the angle between them, so the theta, is 90 degrees, and cos 90 is 0. So that means I dot J is 0. So that's just like a general rule. So if it ever says that two vectors become perpendicular, we know that their dot product must equal 0. So we can write that v1 prime dot v2 prime equals 0. Yeah, so we can use that in this question. So if we start solving this, so we can substitute in the values of v1 prime and v2 prime. So v1i plus vvj dot v2 minus v2i plus vvj equals 0. So once we start expanding this, we can see what happens. So we've got v1i dot minus v2i. So if we go back over here, we can see that if you're trying to do I dot I, so I dot I, we can see the angle between I and I is just 0, because it's the same vector. So and cos 0 is 1, and the magnitude of I, or any unit vector, is 1. So I dot I, which is the same as j dot j, that equals 1. So back here, if we expand this, so v1i dot minus v2i just gives us minus v1 v2. v1i dot vvj, we know I dot j is 0, so that just equals 0. And then we've got another vvj dot minus v2i, that's 0 again. And then we have vvj dot vvj, so that gives us vv squared, because j dot j is 1. Yep, and that equals 0. Okay. So the next thing that we can do is we can work out what vv is. So we can work out what the vertical velocity is using the equations of motion. So we know the equation of motion, v equals u plus at, so that's just the general formula. So in this case we know that the initial vertical velocity was 0, the final vertical velocity is our vv, and the acceleration is g, so like gravity, g. So we can write that vv equals gt. So the whole point of doing this is to work out what t is, so what the time taken is. So if we substitute this value of vv into our equation here, we get minus v1 v2 plus g squared t squared equals 0. And then if we solve for t, so g squared t squared equals v1 v2 t squared equals v1 v2 over g, and t equals sorry, that was g squared. So t equals square root of v1 v2 over g. Yeah, so this is like the main result of doing all this. So the question was asking us to calculate the distance between the particles. So if we go back to our diagram, we can see that the distance between the particles is like between here and here. So we can call that distance s. We'll call it s. and we can see that distance is equal to the distance travelled by the first particle, the horizontal distance travelled by the first particle, so that's from like there to there. We can call that S1, added to the distance travelled by the second particle, so there to there. So we can call that S2. And now that we have the time that it takes for everything to happen, we can work out what those two distances are. So if we go over here, we can say the distance travelled by particle 1. So if we call the S1, that's equal to so the horizontal velocity of particle 1, which was v1. So that's v1 times t. So then if we substitute in the value of t, which was over here, so it's v1 square root of v1 v2 over g. And similarly, the distance travelled by particle 2, we can work that out as well. So we can say S2 equals v2 t, so that's v2 square root of v1 v2 over g. So the total distance, so the overall distance between the two particles, S equals S1 plus S2. Just adding them together, so we have v1 plus v2 square root of v1 v2 over g. Yeah, and that's the final answer.